Okay, so on this one, I'm going to deal with um, routing, some routing fundamentals. Then I'll proceed on to routing algorithms, or which are mathematical algorithms to route data packets across international networks using algorithms like Dijkstra's algorithm, and then I'm going to proceed on to the core protocols of the internet, right? So starting with some fundamentals of the routing process. Now, routing is the core function of the internet uh, because it enables data to be transmitted or to travel efficiently across networks or from source device to a destination device, and it happens to complex networks all around the world, right? So this routing process is essential when it comes to connecting local networks onto regional networks as well as global networks worldwide, right? So the routing process that I'm going to describe just now really ensures that data packets, they follow the most efficient route that is discovered from, routing tables. Ensure that data packets avoid congested networks or avoid congestion, as well as reach the destination or the destination network reliably, right? So what this routing process entails is that it there's a process of basically forwarding data packets from a source device to a destination device over complex or interconnected networks, right? And so we have devices which are performing this routing process, and those devices are mainly routers, right? Doesn't matter what you're going to call it, but the routers which perform this routing process. And those routers, what they do is they're responsible for, examining the packet headers, which I'm going to look at just now. They're responsible for, doing some consultation with the routing tables or routing databases in order to, determine or decide on the best optimal path to transmit the data packets. And this routing process, in terms of the OSI model, it takes place or operates at the network layer, which is the third layer of the OSI model. Remember, the first time I spoke about the OSI model, I said that it has, seven layers. The data link layer, the first layer, followed by the physical layer first, then the data layer, data link layer in the second layer, followed by the network layer, and then there's a transport layer. On top of that, there's a session and presentation, and then a final application layer on top. So it is at the third level or third layer, which is the network layer, right? So the routing process, how does it take place? First of all, it is essential to understand that every data packet that is transmitted over the internet actually contains um, some packet headers or information with it, and the packet headers of interest. Just going to mention a few for now, and then when I get to routing algorithms, and then I will unpack the the packet headers that can be contained in a data packet. But essentially, what a data packet contains is the source IP address of the origin device where the data packet or originates from, right? And that source IP address can be IPv4 or IPv6, and then there's a destination IP address, which again can be IPv4 or IPv6, which is the IP address of the target device or the target network, and then other packets would or packet headers would include things like the protocol type, the packet size, as well as TTL. TTL is the time to live, right? I'm going to explain what that is in just a moment, right? So those are some of the packet headers that data packets contain, right? So the routing process, how it actually works from step by step, and I've already explained that this routing process when I looked at routers as well as modems and switches. All right, if you go back into that video, you will uh, um, you'll come across that routing process that I explained there. But essentially, the routing process starts by the data packets gets to or arrives at the router, and it arrives from a local network, and the local network can be a home network or an office network. Gets to the router, and then the second step is that the routing examines or reads or checks the destination IP address, right? And the purpose of this is to mainly determine where that packet is headed, so the router knows where it's headed. And then after it examines the, the the destination IP address, it then does consultation with the routing table, which I'm going to explain next. Does consultation with the routing tables in order to to determine the next hop. All right. After determining the next hop, um, the router then forwards the packet onto another router, or it can be the destination network itself, right? And so we have this routing process, essentially repeating over and over again until the data packet eventually reaches the destination or the destination network, right? And so then there's the routing tables. Now, these routing tables, what they are essentially are databases which are have been stored in each and every router in the network or across networks all over the world. So you have routers containing or which have these routing tables stored in them or databases stored in them. Uh, uh, the information that is contained within these databases is basically information about the paths to different networks globally, right? And remember that a database is a table, which means there's columns and rows, and there are several key fields or attributes that you'd usually find in a routing table or a routing database table, such as like the destination network. That's one attribute that is usually common in routing tables, and a destination would be represented by the IP address or the subnet of the destination or of the target network rather. And then another attribute would be the subnet mask, and the subnet mask is there to distinguish or define the network portion against the host portion. Remember subnetting? Uh, Go back to that video where I explained subnetting process. So the subnet, defines the host portion versus the network portion of an IP address. Another, a key attribute that is usually common in the routing database is the interface. The interface, that's the router interface, which actually does the forwarding of the packet. Another uh, key attribute is the next hop, which is represented by an IP address. That IP address is usually the IP address of the next router or of the next gateway to send the data packet. And some other attributes would include a metric or the cost that is involved in making that decision on where to send the data packets. And that metric is or the path preference rather is usually based on the hop count. It's usually based on bandwidth. Remember bandwidth? It's based on latency. It's also based on reliability. So those are some of the key attributes or fields that would be common in routing database, right? Now, to put this into context, considering like an IPv4 routing table whereby you have these attributes in that routing table. Let's say you have three destination networks represented by IPv4 IP addresses. The first destination network being 192.168.1.0. The second destination network is 192.168.2.0, and then the third destination network is 0.0.0.0. And I'm going to explain what this 0.0.0 is. Um, that's the first attribute or the three different destination networks that would be possible. and then the subnet mask. Remember, the subnet mask defines the network portion versus the host portion of an IP address. And so you would have, let's say, a subnet mask of like 255, 255.255.255.0, which is, network portion bit of 24 bits. Uh, and then there is the next hop, which would be given by, let's say, an IP address of 192.168.1.2 and so on. And then there's the interface given by S0 and the metric. Now, that's a typical routing database table, right? And what the 0.0.0.0 IP address is, it's actually the default route that is taken, and that it is usually chosen when there isn't any specific routes that exist. And then the metric is based on or the path preference, or the preferred route is based on the lowest metric. So the metric would be ranked, let's say 1, 2, 3, and so on, up to let's say 5, or going onwards and so on. But you take the lowest metric in order to select the best path possible, right? Those are routing tables. And then the key fundamental difference between the routing process versus the forwarding process, because they are two different processes. The routing process involves building or constructing the routing table itself, and then determining the best paths in order to forward the data packets. And then the forwarding process is actually the sending of packets based on the routing table. So in forwarding, the decision is based on the routing table, or the information that is contained within a routing table. And so what routing essentially means is that it is essentially the planning of the journey to a destination network, whereas forwarding process is the actual driving or sending of packets along the chosen path, right? And so there's the best path selection criteria. There's a common criteria which is used by routers or routers in order to select the best path, because routers may be faced, or they may have multiple paths to a destination, right? And so they need to use things like routing protocols as well as metrics in order to choose the best path to a destination network, right? And so there's a common criteria, or the common metrics that are used in all the routing protocols. And one of the key metrics that are considered includes the hop count. The hop count would be the number of routers that packet passes through in order to get to a destination network. Now, a fewer hop count is actually preferred, right? That's the first metric that is considered for the best path. Then bandwidth is also considered, and we have to compare the the bandwidth between different network paths. So higher bandwidth paths would be preferred because they have larger data flows, or they allow more information to be transmitted simultaneously, right? And then the third metric, these are just a few metrics to be considered when selecting the best paths to forward the data packets. The third one is the latency, and so those lower latency or lower delay paths with minimal delay may be preferred, or are usually preferred, for real-time applications like streaming, as well as cloud services and other things like video conferencing and so on. And then the cost as well is also considered. The cost of the administrative weight is also considered, and that's usually assigned either manually, or it's assigned by policy. It's assigned manually by network administrators, or assigned by policy, meaning by routing protocols. And then another key metric that is considered for the best path selection is reliability, and that is through avoiding the network paths which are prone to failures, avoiding them as much as possible. Right, so there is a whole criteria that is followed by routing protocols in order to select the best path, right? And then from there, there is different types of routing. Uh, we classify routing into two types, like static versus dynamic routing. Now, static routing is all the routes are manually configured by network administrators, and this approach of routing, because it's done manually by network administrators, is very simple. It's basic. It's straightforward. It's predictable as well. It's also secured. But the issue with static routing is that it can't be scaled for large networks, right? And any changes would or any network changes would actually require um, manual updates, right? Whereas dynamic routing, on the other hand, is all the routers, they automatically share the route information by using routing protocols, right? And this approach to routing, or to the routing process, is actually very scalable, can be used globally across international networks. It's also very adaptive to any network changes that are observed, right? However, dynamic routing compared to static routing is actually quite complex when it comes to network management, when it comes to configuration as well, right? And so the the different routing protocols which are used to in both of these environments, static and dynamic environment, that the types of protocols, the common ones, based on the routing algorithms that I'm going to look at next. Uh, let's say for distance vector algorithm, routing algorithm, we have routing protocols like the RIP protocol and the IGRP. RIP is the routing information protocol, and then there's interior gateway routing protocol. Right? Those are two protocols which usually use those metrics that I've mentioned, like the hop count, reliability, bandwidth, and so on. And so these types of routing protocols have periodic updates as well. But I'm going to explain what that is just now, right? And then considering link state algorithms, you have protocols like OSPF and IS to IS, right? No, OSPF is the Open Shortest Path protocol, and then ISIS is intermediate system to intermediate system routing protocol, right? That uses a network topology, which I'm going to explain just now, uses a network topology as well as there's these types of routing protocols that have very fast convergence, right? Now, convergence essentially means that there is quick adaptation to any network changes. That's what convergence implies. And then looking at path vector algorithm is the routing protocols which are built around this uh, about around the path vector algorithm is the BGP, or the border gateway protocol, right? And that border gateway protocol actually is used for the internet backbone, and it chooses routes between uh, interdomain routing, right? So I'm going to explain just now what these protocols are, and as well as the different routing algorithms which are at play, right? So the next important thing about routing fundamentals is the wire routing is essentially matters, right? Before I get to or onto how routing actually works on the global scale on the internet. Routing is essential for several things, because routing ensures efficient delivery of data packets across networks, right, from a source to a destination. Routing The routing process that I'm going to explain next is it minimizes things like latency, congestion, as well as network failures as well. Routing process also provides redundancy, and redundancy refers to alternate paths. So the routing process gives us alternate paths in case there are any network failures, right? And on top of that, the routing process is actually highly scalable because it supports millions of networks all over the world, as well as billions of devices everywhere. It's also critical when it comes to both local network communication, including global internet traffic, right? So now the how routing works on a global scale on the internet. What are the steps that are involved to make the internet function the way it functions, right? So first of all, you have the story begins with the local network, right? So where the packet originates, it originates from a home network or an office network. That's a local area network. That's where it originates from, and then from there, we have the access network router. That access network router uh, forwards that packet onto the regional network, right? Remember regional networks, and then next, the regional network router takes over. It forwards or aggregates all the traffic, or regional traffic or local traffic. It aggregates that traffic onto the internet backbone or backbone networks which are international, right? And from there, you have backbone routers, which choose or select the global best path that is available, or the most optimal path globally, using like protocols such as the Border Gateway Protocol, and then in order to determine the best path and forward the data packets to the destination network. And then from there, you have the destination router, which forwards the packet onto a specific subnet, right? And so from there, it's with the end user, the packets or that packet or the data packet is with the end user. And what that means is that the packet is essentially delivered to a specific host address, right? When it's with the end user or the end device, it's delivered to a specific subnet, right? And or host address rather, and which is actually determined or depends on the host portion of the of the target network, or the host portion of the IP address of the target network. And so consider a situation whereby an email is sent from one country to another. So that email goes from, let's say, a local router, and from there it goes to the regional ISP that is around in that region, and then from there it goes to the national backbone. From the national backbone onto submarine cables. From submarine cables, it goes to that country's backbone or international backbone, and then from there it goes to the destination IP or a data center, and then it arrives at the end user, right? So that is the routing process. And so what it means is that the routing process is essentially forwarding data packets from source, to destination. And you have routers which use things like routing protocols in order to determine what, or which use, routing tables rather, in order to determine what the next hop is. And so the best path selection actually depends um, or the best path selection criteria ensures this optimal delivery, all right, based on several metrics like bandwidth, latency, reliability, and so on, and many other metrics. And also you have routing protocols, and our routing protocols are essential because they automate adaptation to network changes. They also automate path discovery, right? And so, the routing process, what it does, it connects all the layers of the internet architecture that I've looked at, and I'm still gonna look at. So it connects access networks, it connects them to the regional networks, and so on to backbone networks, and to data centers, including the internet exchange points, and finally the end user. That's the whole or the complete routing process, or how routing actually works. And then now there are routing algorithms which perform all this routing process. Now the routing algorithms are essentially that I'm going to look at. I've already mentioned them, distance vector, link state, as well as path vector. Now, these routing algorithms are mathematical algorithms. They were also logical in that they're used by routers in order to determine the best path to a destination across networks all over the world, right? So all these routing algorithms, they, they form the backbone of routing protocols. The different types of routing protocols that I've mentioned, they form the backbone, and so that enables basically the internet to be able to adapt to changes or network changes. It allows the internet to adapt to congestion as well as any failures, right? And so the three major types of routing algorithms that perform that routing process that I've just spoken about are, the distance vector, just like we mentioned, and its link state. After that, today is the path vector routing algorithm. Now, the distance vector or the distance vector routing algorithm actually does the computation. It calculates the best path to a destination based on or using distance metrics, right? And so each router in the network, in that scenario, in the distance vector scenario, each router actually maintains or keeps or stores routing distances, um, or tables of distances or metrics to all known networks around, right? So it keeps that record of distances to all known networks that are available, right? And it shares that information, or periodically shares that information with other routers in its neighborhood, right? And so the underlying idea here, or the key idea here, is that the router has to tell other routers what it knows about, the distances to all known networks, and those other routers as well. They have to share their knowledge or the information that they have regarding the best paths to other, you know, uh, networks, right? So, distance factor is really metric based, in that every decision is dependent on the best path to to a destination network is based on several metrics that I've mentioned, like the hop count, the cost, as well as bandwidth, latency, and so on. So it's metric based. That's what characterizes, the distance factor routing algorithm, right? Uh, Distance factor is also what's this? Um, it I remember the point, but just to proceed, the protocol that uses distance vectors I've mentioned is the RIP protocol, and as well as the IG RP, or the Interior Gateway Routing Protocol, right? And those two protocols, the hop count, that is the maximum hop count that is allowed in that scenario, is a maximum of 15 hops, right? And as well as the Interior Gateway routing protocols, otherwise uh, known as Cisco, right? They have, like, they use or composite metrics, meaning that they use bandwidth, latency, uh, as well as reliability combined, right? So that's what characterizes or the distance vector routing algorithms, right? And the point that I wanted to mention is that distance vector has periodic updates between routers, and that essentially means that the routers, they exchange routing tables at regular intervals, right? And so the distance vector is very simple to implement. It's the easiest of the routing algorithms among the three, right? It's very simple to implement. It doesn't require much processing, or it has minimal processing overhead, and it's very suitable for small to medium networks. So it works well in those certain environments where the networks are very small in size, as well as medium networks as well. However, the one thing to note about distance factor is the problem that they suffer from, and that is slow convergence. That means um, updates can actually take time to occur, right? Or the routers take time to adapt to network changes, as well as the other problem is the problem that's known as count infinite problem. And that simply means that the routing loops can occur, which means that you have now the routing process that I've explained, uh, going in endless cycles and so on. So that's the issue with distance factor. And then the other routing algorithm is the link state routing algorithm. Remember the network topology that I said I'm going to explain. Now the link state routing algorithm, what it does is that it actually shares or gives each and every router that's in the network, gives each and every router the full map or the complete map of the network topology, right? So each and every router has a full map of the network topology. All the components are known to each and every router. Now, what that's supposed to do is each router actually does um, the computation or independently calculates the shortest path to every destination using algorithms like Dijkstra's algorithm in order to compute or calculate the shortest path to a destination. Let me just hold this nice into to the shortest path to every destination, and the underlying principle are around the link state routing algorithm is that each router knows the full map of the network, and so by that knowledge or that awareness, it has the ability or the capacity to compute the shortest path all by itself, right? Each and every router has this ability to compute the shortest path all by itself, right? So what characterizes uh, link state is the topology awareness, which means each and every router knows, all the routers or the network links that are available in the network. And it's also characterized by link state advertisement or LSAs. Now, what this link state advertisement is that routers they share um, what the state of the directly connected links is, right? Let's say each and every router has directly connected links to it, so it has to share with other routers what the state of of that directly connected link is. Like let's say congestion, any network failures, and so on. Latency as well as bandwidth and all of that has to share that information with other routers. So have this link state uh, advertisements between routers. And then there's also independent calculation here, which means routers independently compute the shortest path locally, which means all by themselves, and that reduces things like routing loops, right? And so the protocols which use the the link state routing algorithms is the OSPF protocol as well as ISIS. We'll explain what OSPF is, the Open Shortest Path First protocol, and the intermediate system to intermediate system. And so the OSPF protocol, what it does is that it uses algorithms like Dijkstra's algorithm in order to compute the shortest path, as well as it has fast convergence and so on. It also supports like hierarchical networks, and so the intermediate system to intermediate system protocol and the open shortest path first protocol are similar because both of them have fast convergence. They both use Dijkstra's algorithm and other related algorithms in order to compute the shortest path to every destination. And on top of that, they both support hierarchical networks like regional networks from the two backbone networks and so on, right? So those are the typical uh, routing protocols which use the link state routing algorithm, right? So link state actually has fast convergence because each router quickly adapts to any network changes. Link state also is very very scalable which means it accommodates or works well for what's this for large scale uh, global networks, right? So routing or link state also, or it has loop-free paths, which simply means is that since each router performs independent calculation or independent computation, that reduces loops or routing loops or that endless cycle of the routing process. So that's how it prevents or avoids or it has loop-free paths. But however, the link state is tends to be more computational intensive compared to distance vector. It is it requires more memory. It also requires more processing time uh, in order to uh, in order to maintain or to store that network map or that network topology map that is given to it by the link state algorithm, right? And on top of that, there's complex configuration issues or challenges, rather. Let me not say issues, let me say, challenges or as well as management, right? So that's the link state routing algorithm. And from there, there's the path vector algorithm. Now, the path vector algorithm is where things get slightly complicated, right? Because that's suitable or works for and for backbone or the internet backbone, right? That's the core part of the internet or the central part of the internet globally, right? So, at path vector routing algorithm is used. It's used in between in inter or they call this inter-domain routing, or what that means is that the route is used in the process of routing between autonomous systems or AS, right? So what the router is here in this scenario is that they maintain uh, the paths to each and every destination as a sequence of AS numbers, right, or autonomous system numbers traversed, right? And so what the routers in this case, the key idea about routers here is that what they know is that they know the path to a destination. They know all the paths to destination, but however, they do not know what is the distance to that particular destination, right? So that's the key difference. And so, path vector algorithm actually, in this case, the routers maintain path information, which means they not only store the distance information, but they will only store the paths to that particular destination as a sequence of AS numbers or autonomous systems numbers, right? Path vector also avoid loops, right? Which means that the routers examine the paths, and by examining the paths um, that reduces or that prevents routing loops from occurring between autonomous systems, right? So that's a few characteristics of link state, no, of path vector routing algorithms, as well as there's also its use of what's this in backbone networks or in the internet backbone. So they use in the internet backbone as well, or they support large scale inter-domain routing, right? So the protocols which typically use path vector, which are built around path vector, is actually one like the BGP or the border gateway protocol. That border gateway protocol actually uses the path between autonomous systems. It uses policies as well as route or route aggregation between interdomains or between autonomous systems as well, right? And so what path vector is good at is preventing loops between domains or between autonomous systems, right? It's also quite scalable as well, and it also supports policy-based routing. And what that means is that uh, every ISP or an ISP is able to control traffic because of its support of local policy-based routing. That's the advantage. Sorry, there's a fly in here. It's disturbing me. So it uses that policy-based routing in order to, or the ISP rather uses the policy-based routing in order to be able to control traffic flow, right? And on top of that, there is the bad side to the path vector routing algorithms, which means it has actually slower convergence when you compare it to when you put it side by side with link state routing algorithm. It's actually slower within domains, right? It also has, just like link state, it also requires complex, or sorry, it also requires complex what's this complex configuration as well as network management. So that's the the path vector routing algorithm, right? And from there, you um, you consider all of them, right? And so the key point here that I'm trying to make is that modern internet routing actually uses the combination of all these routing algorithms, right? The distance vector, the path vector, including the link state routing algorithm. It uses them for several reasons, right? The path, or the link state routing algorithm, mainly used for internal networks. Those internal networks can be, for example, the OSPF, or the open shortest path between what's this within an ISP's network, or within an enterprise's network, right? And the other thing is um, the path vector. That path vector is used in routing between ISPs, as well as the global backbone, or the internet backbone, right? This fly is attacking. Yeah. So that concludes the routing algorithms, and then from there there's the core protocols, which do all these things, right? The core protocols of the internet. Now the internet functions because of a set of standards that I'm going to unpack from here onwards. It uses this set of standardized protocols which define how devices globally, how they communicate globally, how they transmit data, as well as how they address each other, right? So it sets the rules. All these protocols, they set the rules of how the internet actually functions, right? And so the core protocol suite is the TCP and the IP. Remember the TCP and the IP in the very first video, right? So the TCP, remember, it's transmission control protocol, and the IP is the internet protocol. And so those two protocols, or they represent a suite of core protocols, rather, which actually form the foundation of modern networking, right? So TCP and IP, right? Whenever I mention TCP and IP, it's not a single protocol, but rather it's just a suite of protocols which work together, and according to the OSI model, they work together in order to provide reliable, flexible, as well as scalable communication over the internet, right? And so there's uh, pro- this core suite protocols. They're divided into several layers according to the OSI model, and in the the internet protocol operates, as I've said previously, that they operate at the third layer, or layer three, or the network layer of the OSI model. Then there is the transmission control protocol, which is at the transport layer, or the fourth layer of the ASI model. And then you have other protocols like UDP, you have ICMP, HTTP, HTTPS, and so on. And those typically operate at higher layers of the OSI model. Now, the Internet Protocol, or the IP, right? IP is responsible for several things. One of them is addressing. Other is routing and the delivery of packets from a source to destination across complex networks or interconnected networks globally, right? And so, just like I said, that it operates at the third layer of the OSI model, and in future I'm going to address or unpack the OSI model itself, right? So this IP actually allows or it provides logical addressing. And the logical addressing is important in the fact that it allows devices to anywhere in the world to be able to communicate with each other. And so there are key uh, um, purposes of the internet protocols or of IP, or the key functions of IP that this protocol plays, right? And one is logical addressing. Now, that simply means that IP, or the internet protocol, assigns a unique IP address to each and every device that is connected to the internet. And also, the IP protocol, supports IPv4 IP addresses, which are 32 bits, and also supports IPv6 IP addresses, which are 128 bits, right? And it also uh, helps distinguish between network portion and the host portion of an IP address. And then the other function is the best effort packet delivery. And that is to say that, IP actually does not, when it delivers data packets to a destination, it delivers data packets without any guarantee, right? Which means that data packets themselves can be lost in transmission. The data packets can um, can be delayed, or they can arrive out of sequence or out of order, right? And so this issue of reliability is actually handled at the higher layers of the OSI model, or by the TCP, or the transmission control protocol, right? And there is another function of IP, of the internet protocol, is the process of fragmentation and reassembly, right? And what that means is that often networks have something called the maximum transmission unit limit. And that is to say, let's say an Ethernet cable has like 1,500 bytes um, MTU limit, right? That's the maximum transmission unit limit. That's uh, the limit of an Ethernet, let's say 1.5 or 1,500 bytes, right? And so what happens here, or I'm going to consider that example just now. I'm going to explain what I mean, right? So this process of fragmentation and reassembly, what happens is that uh, the IP address then fragments the packets into multiple or into smaller pieces for efficient transmission, right? And from there, at the destination, there is the reassembly of the packet, which means ISP, no, not the IP rather, the IP reassembles the fragment into the original packet, right? And IP also supports routing, which means that IP allows data packets to be routed uh, across uh, global networks, right? And that simply means that IP actually uses the routing protocols in order to determine the best path, right? It's routing protocols as well as metrics in order to determine the best path to send a data packet. Now onto the fragmentation process, as well as the reassembly process. As I've mentioned, that there is this issue of maximum transmission unit experienced by network. So again, going back to that limit of that Ethernet cable, which has 1,500 bytes. Uh, what the IP does is it fragments the data packet, which is, let's say, the original packet size is like 4,000 bytes, which exceeds the limit of 1,500 bytes, right? So what the IP does is that it fragments the packet, the original packet, into three packets. So the first fragment has, let's say, a limit of 1,500 bytes, right? So, and then the second fragment would have 1,500 bytes as well, and then the third fragment would have like 1,000 bytes, right? And then what happens at the destination is that the IP, reassembles all the fragments, to create back the original packet, or the original packet size, which is like 4,000 bytes, right? And so the key idea here about this fragmentation process as well as reassembly process is that um, all the fragments of the data of the packet, all the fragments actually contain identification. They contain flags as well as the fragment offset. Right, in order to allow proper reassembly at the destination, as well as the, the fragmentation process is actually automatic or it's automated, uh, and and not only being automated, but it adapts quickly to network changes, right? And so this core protocols or the core protocol suite like the TCP as well as the IP. Uh, since I'm focusing on IP or the Internet protocols, which ensures the best delivery or best effort packet delivery, right? Remember the issue was is that IP actually does not guarantee the delivery of data packets to the destination because packets can arrive out of sequence, out of order. Packets can be lost. Packets can be duplicated over transmission. Packets can be dropped in transmission or during transmission or in congestion. They can be dropped, right? And so you have protocols like the transmission control protocol at the higher layers of the OSI model, which handles the reliability of this protocol of the internet, which means that this TCP or the transmission control protocol actually uh, does the retransmission of the packets if case it is in case it is lost or congested or stuck in traffic and so on, as well as the sequencing of data packets. And so this um, protocol or the internet protocol is actually effective when it comes to universal addressing, right? And what universal addressing is, that is giving every device that's connected to the internet uh, an IP address so that it can be uniquely identified globally, right? IP is also effective when it comes to interoperability between different networks. Let's say, or it enables interoperability between different networks like Wi-Fi, um, mobile networks, uh, Ethernet, as well as fiber and other networks in order for the devices to communicate efficiently. You know, also IP actually supports just like the routing process, it supports the large scale or the fast growing pace of millions of networks globally, as well as the billions of devices, right? And so the IP ultimately uh, does is to what's this is ensuring like there's efficient routing and addressing of devices that they can be uniquely identified or they can uniquely identify themselves, right? So I'm going to stop it here and then see you on the next one. Thank you.